Shalom and welcome to the first part of our Unit 4 presentation on the Entity Relationship Model, or CIS 3107, Database Modeling. We will be covering sections 1.4 in our text. In this first presentation, we will learn the main characteristics of entity relationship components. The Entity Relationship Model, ERM, forms the basis of the Entity Relationship Diagram, ERD. The ERD represents the conceptual database as viewed by the end user. ERDs depict the database's main components, entities, attributes, and relationships. Because an entity represents a real-world object, the words entity and object are often used interchangeably. Recall that an entity is an object of interest to the end user. In Unit 2, we learned that at an ER modeling level, an entity actually refers to the entity set and not to a single entity occurrence. Attributes are characteristics of entities. A required attribute, usually bolded in our diagrams, is an attribute that must have a value. In other words, it cannot be left empty. An optional attribute is an attribute that does not require a value. Therefore, it can be left empty. Attributes have a domain. As you learned in Unit 3, a domain is a set of possible values for a given attribute. In the crow's foot notation, the attributes are written in the attribute box below the entity rectangle, see Figure 4.1. Because the Chen representation consumes more space, software vendors have adopted the crow's foot attribute display. Note that the stu_l name and stu_f name and the stu_initial are bolded to indicate they are required attributes of the student entity. The ERM uses identifiers, which are one or more attributes that uniquely identify each entity instance. A composite identifier is a primary key composed of more than one attribute. Attributes are classified further as simple or composite. A composite attribute, not to be confused with a composite key, is an attribute that can be further subdivided to yield additional attributes. To facilitate detailed queries, it is wise to change composite attributes into a series of simple attributes. A simple attribute is an attribute that cannot be subdivided. For example, age, height, or marital status would be classified as simple attributes. A single-valued attribute is an attribute that can have only a single value. Multiple valued attributes are attributes that can have many values. The ERD in Figure 4.3 contains all the components introduced thus far. The car_VIN is underlined in both models, as is the primary key. In the Chen ERM, multi-valued attributes are shown by a double line connecting the attribute to the entity. The crow's foot notation does not identify multi-valued attributes. As the car_color is a multi-valued attribute is implied in the car entity. The car entity's foreign key, FK, has been typed as mod_code, which is listed purposely at the top of the attributes in the entity. Multi-valued attributes are attributes that can have many values. For instance, a person may have several college degrees. A household may have several different phones, each with its own number. A derived attribute is an attribute whose value is calculated or derived from other attributes. The derived attribute need not be physically stored within the database. Instead, it can be derived by using an algorithm. Although the conceptual model can handle many-to-many relationships and multi-valued attributes, you should not implement them in the RDBMS. Remember from Unit 3 that in the relational table, each column and row intersection represents a single data value. So, if multi-valued attributes exist, the designer must decide on one of the two possible courses of action. One, within the original entity, create several new attributes, one for each component of the original multi-valued attribute. For example, the car entity's attribute car_color can be split to create the new attributes car_top color, car_body color, and car_trim color, which are then assigned to the car entity. Or 2, create a new entity composed of the original multi-valued attributes components. This new entity allows the designer to define color for different sections of the car. See Table 4.1. Then, this new car_color entity is related to the original car entity in a one-to-many relationship. Using the approach illustrated in Table 4.1, you even get a fringe benefit. You can now assign as many colors as necessary without having to change the table structure. The ERM shown in Figure 4.5 reflects the components listed in Table 4.1. This is the preferred way to deal with multi-valued attributes, creating a new entity in a one-to-many relationship with the original entity yields several benefits. It is more flexible, it's an expandable solution, and it is compatible with the relational model. Figure 4.6 shows a derived attribute in the Chen notation by a dashed line that connects the attribute and the entity for imp_age. The crow's foot notation does not have a method for distinguishing the derived attribute from the other attributes. Imp_age may be found by computing the integer value of the difference between the current date and the imp_dob. Derived attributes are sometimes referred to as computed attributes. Computing a derived attribute can be as simple as adding two attribute values located on the same row, or it can be the result of aggregating the sum of the values located on the many table rows. The decision to store derived attributes in a database table depends on the processing requirements and the constraints placed on a particular application. Stored derived attributes save CPU processing cycles and data access time, which make a data value readily available. These stored values can be used to keep track of historical data. The disadvantages are that these stored attributes require constant maintenance to ensure derived value is current, especially if any values used in the calculation change. Not storing the derived attribute saves storage space, and the computations always yield the current value. While this has the disadvantage of increasing the use of CPU processing cycles and increasing data access time with additional coding complexity to the queries. In summary, the ERM uses ERDs to represent the conceptual database as viewed by the end user. The ERM's main components are entities, relationships, and attributes. We have also discussed different ways to implement multi-valued attributes and derived attributes within the ERM. Thank you for watching our Unit 4 Part 1 presentation. The diagrams and content of this lecture were derived from our textbook. For a more detailed treatment of these concepts, please review pages 117 to 124 in our text.